So one of the difficult questions that I get all the time from companies who want to do moisture sorption isotherms is, should we do it the classical way? The classical way is to use desiccators, and you have different saturated salts that you make for each one. So it's a salt solution in each desiccator, and then you put a sample in to the desiccator, and generally you use a triplicate sample and weigh it. Also take part of that sample and measure the initial water content by Carl Fisher. And then you'll have a series of salt solutions all the way from about 11% to about 85–90% in there. And there's, if you go to some tables, you can get these, the water activities. It's a saturated solution, so it's actually a slurry at the bottom rather than a solution by itself. So that way, if the sample's picking up water from it, it's not going to change the water activity of it. So like sodium chloride slurry is 75% relative humidity. That is a cheap way of doing it. Don't cost you very much. In fact, we don't even use desiccators because they're about $80 a piece. We use fish tanks from Walmart, okay, about 5-gallon ones, and we make a plastic cover for the top and get a couple of bricks or stones to hold it down, and we put a platform in the bottom that we make. We get some acrylic thick shelf type of thing, drill holes in it so there's air, and then glue in 4 feet on it so that it sits above the solution there. The advantage of a fish tank is that you can put a lot more samples in there, so you can run 3 or 4 different kinds of samples at the same time. The alternative to that is the DVS. Let me just go back. It's this instrument here. This is about $180,000, and it's only one sample. Or the old Decagon AquaSorp, which again is only one sample, and the newer one is only one sample. And here what you're doing is you're programming the sample to higher and higher levels of humidity, and it's all automated in there, and you can set the steps by going to the next humidity and waiting until equilibrium occurs, and that's just watching the weight of the sample, and the computer is constantly collecting that data, and it will automatically, if you say no more than a 0.01 change in grams of water, would be our next step, and it would step through that. You can also set a minimum time between the steps, and what happens is that higher water activities, you get a greater change in moisture content, and so sometimes you want to program it differently when you're down in the bottom of the isotherm versus at the top, because it's going to think it's at equilibrium, but it's not in there, and that's a real problem in there. So the Decagon newer one, you can put a sample up to 5 grams. If you do a 5-gram sample, it's going to take hours and hours to equilibrate. Okay, so that's one of the problems in that. It'd be better to have a thin layer in there. And if you have a heterogeneous sample, that's not good to have a very thin layer because you may not have all the stuff in there. You can use it by initially drying in the instrument We don't do that. I just put it in at the water content and it's at. And so it may have losing water in the beginning and then gaining water after that. And we just do the initial drying by using the Carl Fisher so that it checks that for you. As I said, you can change the steps and then measure the humidity. It uses a dew point device, which is very accurate. You can vary the flow rate of water over the sample. The faster the flow rate of water, the faster the gain is going to occur in it. And typically what they recommend is that equilibrium is when the relative humidity difference over X minutes, and X minutes would be up to 2 hours, is not changing by more than 0.5%. The problem is the surface of the sample is going to equilibrate fairly rapidly, and therefore it's going to slow down because now the driving force to pick up water is going to be slowed down, and you may have dry material underneath if you have too thick a sample in there, and that's a real problem itself. Price, $30,000. Not too bad. Here is some studies we did. This is with plain corn flakes. The static is these data points here. So these are the fish tank values. The blue dot is the AquaSorp, the older one, because we did this on the older one. That comes closer to it. And this is the DVS run, or no, I guess there's 3 different AquaSorp runs in here that all are outside the static values. Okay. If we grind the sample, here's the AquaSorp in the blue, and the static is in the black, and it's hard to see it there, but it's almost exactly on the line. 1 data point off over here. The green one here is, and the colors don't show up right, but I think the green is the whole flake, whereas the static is the whole flake here, and the ground flake DVS is the orange, which comes pretty close to it in there. So if you grind, you get a better comparison to the static values itself. This is gum arabic, and static is the purple. You see at the higher level it's separated out, although the DVS came pretty close to it there. There's a little difference here, a little weird blip in the isotherm, which I think is crystals of something that are dissolving at that point, going into deliquescence. This is sodium chloride and a blend of sodium chloride and potassium chloride, and basically this one is KCl. What you see is that at a water activity of about 0.86, it deliquesces and goes into solution. This is NaCl, and that goes into solution around 72% relative humidity, or water activity is 7.2. And the blends are a little bit lower than that. It's one interesting thing. If you take 2 different crystals and mix them together, the deliquescent point is now lower than either of them. And there, one of my former graduate students who is a professor at Purdue did some of that work in there. And there's an equation that I've developed that's really based on the product of the activities of each. And so you take the activity of water, of KCl times the activity of the NaCl, where they go to deliquescence. The mixture is at the product of those two numbers, which is interesting. I'm going to skip over that. Another method is to use freezing point. And there's an equation here. It's based on the Raoult's law that we talked about before. And what we find is for freezing that the change in temperature, or the decrease in temperature at which the mixture freezes, is minus 1.86 times the effective moles per divided by 1,000 grams of water. And so that will give you the water activity, and here's another equation that you can put it in there to convert it to water activity. And so it's basically from Raoult's law that this is. And then the other methods are NMR, IR, and dielectric. Same thing as with the moisture content. You can make calibration curves as a function of water activity or as a function of moisture content, and do it that way. All right, switch. I want to do something first. I have 2 tickets for the hockey game tonight. These are $45 seats. Okay, so they're good, really good seats. So if you're interested, write a number between 1 and 50 on a piece of paper and hold it up. Give me a piece of paper so I don't cheat. Okay. Yeah. Question? Oh, hold it up. Hold it up. Okay. Okay. So here's mine. 44? 43. There you go. Oh, 2 43s? Okay, that's it then. Yeah, I did. Do you want to go to the hockey game? Look, it's ice hockey, so it's water involved. Pass these back. I'm going to tomorrow night's game, so. All right. So we get this information of water activity, moisture content. One of the big questions is, what do we do with it? Well, having that isotherm gives us some physical properties and biological properties that are important. For example, it will give you information about physical stability in terms of either texture or caking. We know that products may cake if they contain sugars at about a water activity of 0.3 to 0.4, and that crisp things will go from a crispy state to a non-crispy state at about 0.45 water activity. So that's just a useful thing. Microgrowth. What do we know about microgrowth? I don't have any other tickets, though, for that. Well, we got molds, we got yeast, we got. So what is it then?
For mold and yeast.
0.6. 0.6. No growth below 0.6. Unfortunately, in some of the early microbiology books, they said that a food was safe below 0.6, and they never realized that many organisms have resistance to, they go into hibernation, at lower water activities, including pathogens like salmonella, and that says that you can't assume that a dry product is safe. In fact, one interesting thing was, it's 2 years now ago that General Mills had an outbreak, and it was traced to flour that they made that was out in the field already. 10 million, they had to recover from the retail market 10 million pounds of flour in those bags and then burn it, because they decided they weren't going to test it to see if you could isolate, safe parts of it. And I don't think there was very much flour that was bad, but that was there. Dr. Anor and I are working on a cold plasma methodology to pasteurize in a dry state. I mean, we could pasteurize easily by mixing all the flour with water and then heating it, but then you change the properties of the starch, and you don't want to do that. Yeah. So that was difficult. Chemical reactions, we know that there's a level which we call the monolayer, that below that, chemical reactions that take place in the water phase do not occur. So we need now a methodology for calculating that monolayer, and I'll show you that. We use these isotherms in designing of IMF, and then back in 1965 I came up with a methodology, mathematical model in a spreadsheet that if you know the isotherm and you know the permeability to water for your package, it will give you a time to given moisture content that could be a critical moisture content, let's say 0.6, if you were interested in mold or other organisms like that. So we use them for drying predictions, for shelf life prediction, general storage predictions in terms of shelf life testing, mixing of dry ingredients. One of the best projects I ever had was from the Almond Board of California to come up with making mathematical models for trail mixes in there. So if you have the isotherm for each of the ingredients, like nuts and then dry fruit that's in there, and other things, sometimes crackers, little pieces of cracker and stuff. And if you have the isotherm and measure first the diffusion coefficient for water in each of the products, then you can make a prediction of the shelf life of the product. What would be the key thing that would cause consumers to not want to eat it anymore? Let's say you have nuts and raisins together. Stale, meaning? Soggy what? Which one is going to get soggy? Nuts will get, usually they don't get soggy, they get mealy. Mealy is a better word for it in there. And the raisins get hard. Okay? And it depends on the ratio of raisins to nuts that you have in there that makes a big difference. One big thing that people are doing now, you see more and more of that, is the fruit pieces are covered with chocolate, which is a very good barrier in there. So that really extends the shelf life of the product, and kids like it better. It's not a healthy food. Well, it is, maybe is. So this is a typical type 2 isotherm. that we have. You'll see these slides. These are my older programs, which are for a Mac, and it doesn't work on today's computers, the programs. So I do have Excel spreadsheets, and I'll show you some of those as you go along. This is one of them. You put in, for each of the water activities, you put in the pan mass, the pan plus the initial weight, pan plus the final weight, and then it automatically, and you put what water activity you're going to put it at here. It will calculate, or you have to put in the initial moisture here. You put in the final moisture, and then it calculates two terms here, activity over 1 minus activity times moisture, and activity over moisture, and these are going to be used in graphing the material. So the BET, isotherm equation, Brunner, Emmett, and Teller, its derivation came from nonpolar gases on nonpolar surfaces. That's not water in food. It requires that you decide that the first layer has some excess enthalpy of absorption, and this is the typical vaporization thing. So we call it isosteric heat, and Q sub S is the excess enthalpy. So we assume that every water molecule is going to have exactly the same heat absorption, which is not true, because the binding to an NH2 group versus the binding to a hydroxyl group or to an acid group is going to be different in there. We then assume that the second layer does not interact with any of the water, and so it just has the heat of vaporization and no excess enthalpy, which is probably not true in there. As I said, it assumes all sites have similar energy. It also says that there's no across the surface interaction between the water molecules. And one can derive this equation from kinetics, from statistical mechanics, and from thermodynamics. And people have derived it different ways. So it's not a bad equation, but technically it doesn't apply to food and water. Okay. This is the equation. This is the BET equation. Activity over 1 minus activity times M, the moisture content, is equal to 1 over M0. M0 is the monolayer. C is the heat constant. And then plus C minus 1 times M0 C. So we have two constants, the monolayer and C. We have two variables, moisture content and water activity. So this basically is a linear equation. Y is this first term here is equal to I, the intercept, which is this term here, and S, which is this term here, times the activity of the thing. So, and the C can be decomposed into this product. E is equal to Q sub S, the excess enthalpy, divided by R times the temperature in Kelvin. So, you plot Y versus X. So Y is this A over 1 minus A times M, and X is the water activity. And so you make this plot here. The intercept then is 1 over M0C. The slope is C minus 1 over M0C. So basically you take these two things and divide them. You find that the monolayer is equal to 1 over intercept plus slope. And then from this equation, you can calculate also the value of C. And so my spreadsheet does that automatically. All you need is that slope and the M0. So here's your salts. Here's your water activity at those salts. Here's the moisture content that the product reached after sitting in the desiccators. And here's A over 1 minus A divided by M. So this column here, you then plot this column, A over 1 minus A times M, which is the y-axis. You plot that versus water activity, and you get a straight line, generally no higher than a water activity of about 0.55. Above 0.55, you get significant water condensing in pores. The little pores, the small pores, it's also going to condense at lower levels, but the volume of those pores are small compared to the bigger pores. So that's a critical thing. And you see R square of 9.2, not too bad for this. And that's one sheet in my spreadsheet set that you get, the workbook. The next sheet takes this and does the calculations and puts the calculations in here, the monolayer value and the C constant in the thing. Generally, for a type 2 isotherm, you get a C that's between 2 to about 50. Okay. So if the Q sub S, the excess enthalpy, is about 15,000 calories per mole, then C is going to be equal to 13.2. And that's typical for water vapor in protein systems and carbohydrate systems. If you have a large C, 100 to 200, that's chemisorption, and you're going to get a different type of isotherm. We call it type 1, and I'll show you that in a minute. It's more what we call a Langmuir isotherm. And then C, if C is less than 2, then it's basically the excess enthalpy is close to 0. Okay, and that's more for type 3, which is the crystals. So you get very little absorption until you get to the deliquescent point. What we do know is that moisture does affect the enthalpy. So if we calculate those enthalpies, what we find is that decreasing moisture content, we have a steeper slope, so a higher Q sub S in there, and this is log of water activity versus 1 over Kelvin. This is a typical enthalpy type of calculation. And what we see, the Q sub S, or total, follows something like this, which is really weird, and nobody's really understood why that works itself. At high moisture contents, high water activities, your excess enthalpy disappears, and it's mostly the heat of vaporization for the condensation of the water itself. So here's typical monolayers. Somewhere between about 4 to about gelatin, which is a high one, to about 9 in there. Good question is, why are they different? Any answer? See, it's a good thing I didn't use questions. Well, it depends on the number of hydrogen bonding groups in a starch or a gelatin in there. Generally, you have, which is interesting to me, higher ones for protein, but milk, here's another milk fat down here, but meat and potato is starch. Coffee is mostly carbohydrate in there. Cocoa is low, but I think that's because it's got fat in it, and so it's just diluted. If we compared it on a non-fat basis, it probably is closer to that. So that's why that's low. The same thing with beans. We can also calculate something called the surface coverage. This assumes that you have a one-layer lake throughout the whole system. And that came from the hydrophobic binding work. So basically, that's meters squared per gram. So you take the monolayer, divide it by 18 to convert it into moles, multiply it by the number of molecules per mole, 6 times 10 to the 23rd, multiply that times the angstrom squared per molecule, so the area of a molecule of water, times 10 to the 20th, which is the meter squared over area squared, so that it brings the thing. So it comes down to a very simple thing. The surface area is monolayer times 3.5 times 10 to the third, and here's the area of a water molecule. And for most foods, we find that it's between 150 to 200 meters squared per gram. So that sort of gives you a picture of what you might think of it as related to the pore size distribution in your system. The more smaller pores you have, and for a given quantity of water, that might give you then a higher area throughout the whole thing in there. We don't know the real answers to that. A lot of people also do a liquid nitrogen BET calculation. There's devices for doing that. You're measuring it at liquid nitrogen temperatures. And when you do that for a food material, or even for other materials, you get a surface area of around 2 to 5, very low levels. Okay, I don't know, what do you get for your char? Or you haven't done that? 5 to 10, okay. So that's pretty low compared to food. We'll be doing an isotherm in the next couple of weeks and make the comparison there. I just think there's so many assumptions that are made that with using water, in an equation that's not related to water, but it works. It works because we know if we make our product close to the monolayer, we get the longest shelf life for dehydrated products. Okay, and that there's very little reaction occurring, let's say, for things that are going to degrade in water, and they're like aspartame. That's some of the slides that I showed you earlier. Now, what happened is in 1965, there was a group of us who met in Scotland. What time do we end? We got plenty of time. We met in Scotland and said we should put together some kind of organization that would put together a meeting every 2 or 3 years. Okay? And so I was beginning, that meeting was the first year I was an assistant professor. I went to that meeting and I got on the committee to do that. We had our first meeting in 1974. In fact, I should have put that slide in here, the picture of all the people at the meeting in there. And we decided, at that meeting, we looked at what do we got to do with this whole thing called water activity. Because there was a battle between the microbiologists and the chemists. Very little work had been going on in the chemistry area. My lab was one of the few that was doing that at MIT. And we wanted equations to help us. And so we had people come in and talk about these equations and how good they are. We found an equation that was built upon the BET called the Guggenheim-Anderson-de Boer equation. It had a third constant in it, so it made it more difficult to solve. But it basically, this third constant, the case of B, is generally less than 1. And it's really related to surface interaction, so the monolayer going into multi-layers in there. And if KB is equal to 1, then this equation is the same. If you rearrange it, it's the same as the BET equation. And so we had a lot of people looking at this, and other people wanted to have different or better equations. It ended up that published in the food field, there was 275 different equations. Okay? A lot of them came out of ag engineering departments because the ag engineers wanted an equation named after themselves. So they put their name as the equation name. And a friend of mine at Wageningen University in the Netherlands took those 250 equations and basically showed that you could take them down to 12 different equations, because if you just rearrange things, and that most of the equations, I'd say that 85–90% of them were not based on any theoretical thing. They were just curve fitting. So if you did if you take your water activity, moisture content data, and use a polynomial, a 6-power polynomial, you get a beautiful line. It fits perfectly. I use that to draw the GAB through the thing, and but it doesn't. It's not a GAB equation. The constants have nothing to do with anything. So what we say for using the GAB, you can use all the data. You need at least 5 points to get a good calculation of it, and there's a polynomial solution to the thing. So here's our equation. We can rearrange it into this form, which is a polynomial. So you've got a constant, 3 different, so times a constant times a squared, and then another constant at the end. So basically a over m is equal to alpha times a squared plus beta times a plus e, which is the last term on the end here. And then you could rearrange this whole thing and solve it. Everybody makes mistakes when they try to solve it on their own. What I do is I plot a over m times water activity, and go back again here. You've got a over m, which is y, and you've got water activity squared, water activity to the first power, water activity to the 0 power. So that's, basically a 2-parameter polynomial. The solution is here. The KB is equal to beta squared minus 4 times alpha times E over 2 alpha, and this is minus B. So these are the 3 things that you solve for from the equation, and this is the term here. So you got the alpha, beta, and eta, these 3 constants, r squared 9.7, pretty good. This is the same data that I showed for the for the BET plot, and then so you put in the alpha, beta, eta here, and then it calculates the K value, the C value, and here. So you see C is 2.55 here. In the BET, it's 2.9. Moisture monolayer 0505, and this is 0565. So close. They're really close to each other. And it's nicer because you use more data there. And then you now can set this up with the alpha, beta, and eta, and you can take 0.1 units, and it will draw the plot for you here, and these are the actual values you've measured in the desiccators. So it fits pretty well to do that. So you can convert the polynomial, the 2-parameter polynomial, into the equation for the GAB. And then I have a one page where goodness of fit, comparing the GAB prediction to the moisture content that actually measured, and it'll give you what is a p-value. If it's less than 5%, then you've got an excellent fit to the curve. So that's the best part of it. So here's the mushrooms isotherm, and here's some of the calculations from that it's GAB parameters. I'm not going to bother with that. So what other kind of equations? Over a small range, well, not a small range, over a range with many products, you can get a straight line. So if you're going between 0.1 to no more than about 0.65, you've got a pretty good straight line with an R square of 9.7, which is not too bad. This is the way I solved using this. I solved it for dry products, water activity 0.2 or less, picking up moisture at, let's say, some given outside humidity, and you don't want to go above 0.6, then you can use this as a, and that gives you a nice solution to the packaging equation. So this is what it looks like on the graph. Here's a straight line portion. It's a little bend in it, but not too bad an error. And it just solved a big problem that the industry had. They had no way of predicting shelf life. And this basically solved that problem for the industry. On the other hand, the other way of doing it is if you don't want to go above a water activity of 0.6, you work it backwards to tell you what film permeability you should be buying and using for the package. And that became a big, powerful tool for the packaging people. So here's some other equations. This is linear. Oswin, this equation here. Mizrahi, one of my postdocs, he wanted one in his name, so I let him do that. So it's a very simple A and with the two constants and the moisture here. Kuhn, this one I love. It's the log of the minus log of 1 minus water activity versus the log of C plus B times the log of M. So take a couple of logs on both sides of the equation, you're going to make a straight line. Okay, it has no real meaning at all in there. And then just down here, just going through there, none of them are really very useful. This is not Dr. Dave Smith who did it. No, it's not. And then lastly, I've just put it here for a component thing. Let's say you have component A and component B, and they both have different initial moisture content. So I didn't put the dots on here. So let's say A had a moisture here, B had a moisture content here. You can draw a isotherm for the mixture, okay? And simply at any given water activity, the fraction of solids in A to the total solids in the system times the moisture content at that water activity plus F times M for that. And if you have 10 units, you can go all the way out. And that will then tell you for that given water activity, the imagination moisture is that value there, which is for the mixture in here. And so you go up the scale to do that type of thing. And you can get now the mixture moisture. And then if you know the total moisture in the product, you can go over here to, this is the moisture here, and then read down what the water activity would be at equilibrium. So this would tell you that they would all equilibrate to the same water activity over time. That's the important thing from thermodynamics that we said. And if it's going to be a high water activity, then for one of the components that may be too high. So then what you do is you start playing with the equation to go to different ratios of solids between the two of them, and you can get solution. I put an example of that here. I'm not going to read through these numbers, but it just gives you an example of it. So we got what, 3 more minutes? 4.5? Okay. So I hope you've learned something the last 3 lectures. It's an interesting area. None of this was known in my undergraduate career. I mean, we just nobody was working in these areas, and this except for moisture content. That was the